Welcome everyone to today's statistical seminar. It is my great pleasure to introduce Thomas Berrett from University of Warwick. And Thomas has worked on all kinds of exciting topics, including a lot of permutation tests, independent tests, non-partial statistics. And recently, he's also working on a lot of problems in differential primacies and like change point detections. And Tom received his PhD from University of Cambridge, working with Richard Samuels. And then he did a postdoc also at Cambridge and also doing a postdoc with Christina Butosia. And today he's going to talk about a very exciting topic on the optimal rates for independent testing via permutation methods. And before I pass to Tom, I would like to remind all the audience that you have 3 ways you can ask the questions. You can either use raise your hand and I will allow you to speak so you can directly ask, or you can type in the chat box or using the Q&A function, so that you can just type your question there. And I will monitor the question and raise that to Tom. So without further ado, Tom, the floor is yours.
Thank you very much. And I'd like to thank the organizers very much for the invitation. I'm very happy to be able to speak here today. And yeah, I'd like to just emphasize that point. If you want to ask questions at any point, please do feel free. I'm very happy to be interrupted. So yeah, today I'm going to be talking about independence testing. And in particular, I'm going to be talking about permutation testing, and we're going to be studying independence testing in a kind of Minimax framework. So to go right back to the beginning, often when people talk about independence testing, they will start with a discrete problem. This is perhaps the way in which people first come across independence testing, is within the context of a contingency table. And the simplest version of this problem is simply to test whether rows and columns of an independence, or rows and columns of a contingency table are independent. This is very simple, and we simply want to test whether whether or not a matrix factorizes. This is quite a simple problem to test. There is one solution to this problem that is extremely well known, perhaps one of the most widely applied methods in statistics, and that of course is the Pearson's chi-squared test. I'm sure you've all seen this before, but I'll just remind you, this is the test statistic that you would calculate to do this test. And it is known that for a fixed distribution and for large sample sizes, then the distribution of this test statistic is approximately chi-squared. So we can implement a very simple, very fast test of independence with discrete data like this, just by doing the chi-squared test. Of course, it's also very well known that this test is not perfect. It kind of has some drawbacks. There are all of these rules of thumb about when you can and when you can't apply the chi-squared test. You need a large number of observations. No cell can have too few observations. It's not always clear whether this can be applied in practice. And the reason for this is that it's asymptotic null distribution. The chi-squared distribution, the convergence to this distribution is non-uniform. So for any fixed distribution for a large sample size, we will have an approximate chi-squared distribution. But equally, if you give me any sample size, I can always find some distribution of the data for which the test statistic is far from being chi-squared. So if we consider this sequence of distributions here, so we say that we just have a simple 2x2 table where this probability P tends to 0 as n goes to infinity, then actually the limiting distribution of the test statistic here is more like a squared Poisson random variable rather than a chi-squared variable. And what that means in practice is that this chi-squared limit is not valid. And in fact, we can have type 1 error much higher than we would like to have. So just as a very simple example here, imagine that we wanted to test independence at the 1% significance level. Actually, we can construct examples where the type 1 error of this test is over 10 times as large as the nominal level. Now, of course, this is something we want to avoid. This is obviously an extreme example, but what this is showing us is that you can't always rely on this test to give you valid results. Of course, this is just very simple in the discrete setting. Often, when people study independence testing, when statisticians study independence testing, it's more often studied in the context of continuous data. This is a much more interesting setting for us to study. There are some equally classical methods for solving this problem. So for example, we have things like Pearson's correlation, which is from around the same time as the Pearson's chi-squared test. And of course, this measures linear relationships between the data. We have things like Kendall's tau, which are rank-based methods, which go beyond measuring linear relationships and are able to measure any kind of monotonic relationship between data. And then we have things that are a bit more sophisticated, things like Hoeffding's D, which are also rank-based, but which are able to detect non-monotonic relationships between variables. So as a very simple example, if you look at this plot here on the left, then this is a situation in which Pearson's test and Kendall's tau will both perform very, very well. But on the right here, this is a situation in which they'll both perform very poorly. They will almost always fail to reject the null hypothesis here, whereas something more sophisticated like Hoeffding's D will succeed. Of course, this is very simple. This is univariate data, or we're comparing two univariate variables here. When we consider a more modern setting where we have multivariate data, the situation becomes much, much more complicated. There are many, many ways of measuring dependence between two random vectors. And as a result, there are many, many tests of independence. I've listed just a few here. And so perhaps some notable ones are these rank-based tests here. So I said previously that Kendall's tau and Hoeffding's D are examples of rank-based tests. Now in univariate data, it's fairly straightforward to use a rank-based test. Oh, I mean, it's not easy, but there are many methods for coming up with rank-based tests because the real line is of course ordered, and it's easy to talk about the ranks of data for univariate data. But when you come to studying multivariate problems, that becomes much more difficult. There's no canonical ordering of R to the D. And so it's much harder to come up with what we call rank-based tests in multivariate settings. Moving away from rank-based tests, there are many things like the Hilbert-Schmidt independence criterion or distance covariance, which are more like kernel methods. And there are many other methods as well. And what I hope this shows is that this is a very complex and interesting problem that requires a lot of study. Of course, when you've got this many different tests, a natural question arises, how do we compare these tests? How can we tell which one is better? Which one should we be using in any given scenario? And of course, that's a very difficult question to ask because certain tests are appropriate for certain situations and other tests are more appropriate for other situations. But I'm going to try and present one way of measuring the power of a test. And we're going to adopt a kind of Minimax framework. I'll come on to that later more. But I'll just say to start with, we're going to, there are obviously two types of error when you're talking about hypothesis testing. There's type 1 error and type 2 error. I would argue that we're only going to consider tests that control the type 1 error. So first of all, we're going to ensure that our tests are valid. And then once we have valid tests, we're going to look for the most powerful test. And what this work is about is showing that both of these things can be achieved with permutation tests. Okay, so I'm sure that many of you are familiar with permutation tests, but just as a quick recap, these are a randomization approach that we can use to get critical values for hypothesis tests. In particular, they can be applied to independence testing. If you look at this data set pictured on the left here, we have data that exhibits clear dependence between the X and Y variable. Now, what we can do is we can apply a uniformly random permutation to this data, and we can get a simulated data set like this one shown on the right, where there is no clear dependence between the x and y variable. Of course, if we're studying the dependence between two variables, then we observe pairs of variables x and y, and it's very important that these variables are paired, because all the information on the relationship is in the link between these two variables. What we do when we apply a permutation to this data is we simply mix up all the y variables so they're associated to different x variables, and thereby destroy the dependence between the x and y variables to simulate the null behavior of the data. And we can do this many times. We can calculate test statistics on the true data set and the null data sets, and we can compare them in this way to get a p-value. It's a kind of standard calculation to show that this p-value is always valid. So without any assumptions at all, apart from assuming that the data is IID, we can show that this test controls the type 1 error at the nominal level exactly. So given any test statistic, we can use permutations to come up with a critical value, and we can get a test that is valid without any smoothness assumptions or any other assumptions on the underlying distribution. So if we use a permutation test, then we can ensure validity fairly straightforwardly. What's harder to do with a permutation test is to study the type 2 error. So if you think about it, actually, how would you analyze something like this? We're actually applying quite a complex procedure to our data set. We're calculating a test statistic. We're then randomly permuting the data many times and recalculating lots of test statistics and computing comparing the true test statistic to all these null statistics. That's quite a complicated procedure. Höfting, of course, who was a very clever man, managed to come up with a way of studying the power of these tests, and he came up with this result. And this result is the basis for many studies of the power of permutation tests. So what does it say? It says that if you take some sequence of distributions, so typically these are distributions that are going to be converging towards the null hypothesis, so where the dependence becomes weaker and weaker with larger sample sizes. If we have such a sequence and we can find some asymptotic distributions, so if we can find the asymptotic distribution first of our true test statistic under these distributions, and if we can find the asymptotic distribution of a pair of test statistics calculated on permuted data sets, then we can read off the limiting power of the permutation test like this. This is a very nice result, and it says that we can calculate the power of permutation tests at least asymptotically. One nice byproduct of this actually is that often you can see that the asymptotic power of the permutation test is the same as the asymptotic power of a test that knows exactly what the null distributions of the data are and uses those to come up with the critical value for the test. So this is a very interesting result. Actually, though, what we're going to do in this work is we're going to look for more uniform power results. So we're going to be studying we're going to be looking for tests that can be proved to have power uniformly over whole sets of alternative distributions. The previous result is about asymptotics and a fixed sequence of distributions. We're more interested here in uniform power. We're going to study this within a Minimax framework, and we're going to show that a permutation test can also have very good performance in this sense. So as well as the nice asymptotic results, we're also going to show that it can be Minimax rate optimal. Okay, so just to give an outline for the rest of the talk, first of all, I'll formalize the problem. I'll introduce the assumptions that we're going to impose. I'll introduce the Minimax framework that we're going to work under. Secondly, I will talk about the specific test statistic that we're using. So I've talked a lot about permutation tests, and I haven't said what specific test statistic we're going to be using. So I will talk about that afterwards. This is going to be quite a general test statistic that can be applied in lots of settings. So I will specialize it to discrete cases and continuous cases and talk about the results that we have there. Next, I'll talk about some lower bounds. So I'll show you that we have matching minimax lower bounds in the continuous case and the discrete case. And I'll talk a little bit about how these are consequences of a general result. And finally, if I have enough time, I'll talk a bit more about kind of distributional results. So when we talk about rates of convergence, this is of course all up to constants. And you can establish these results by looking at first and second moments of certain test statistics. Actually, we can push this a lot further and we can come up with more distributional results, which are a bit like finite sample versions of Hoeffding's result. And I will talk about that towards the end of the talk. Okay, so to start with, I just need to formalize a few things. So of course, we're going to assume that we have IID pairs x1, y1 up to xn, yn. They're going to take values in some product space x cross y, and we're going to construct tests of the null hypothesis that x and y are independent. I'm going to let curly p0 be the set of all null distributions. So the significance of this is that I'm not going to impose any assumptions at all when I ask for the validity of the test. I'm going to ask that a test be uniformly valid over the entire null hypothesis. So we're not going to require any smoothness assumptions for our tests to be valid. As I've said previously, all permutation tests fall into this set. So this is an interesting class of tests. And it's those tests where you don't need to worry about type 1 error control at all. Although we don't need any assumptions to control type 1 error, actually, in general, you do need assumptions to control type 2 error. We'll have a formal result stating this later, but I hope it's kind of intuitively clear. At least with continuous data, there are so many different ways that two variables can be dependent that it's impossible to have uniform power results without restricting the class of alternatives in some way. And again, I will formalize this later on. You can probably tell from the notation that this is the general framework encompasses a lot of different settings. The main examples I'm going to be interested in are primarily with continuous data, but there are also some interesting things to say about the simple discrete problem. If you want to see other examples, and you can go to the paper. So for example, we have something about infinite dimensional data in the paper. Okay, so then how do we introduce the Minimax framework? So we're going to have some class of alternatives, or some class of distributions that we're going to consider. So these, in the continuous case, these are going to be distributions that satisfy some smoothness condition. And then we can define a class of alternative hypotheses as follows. So we can look at all smooth distributions which are separated from the null hypothesis with respect to this measure of dependence here. So this is quite a standard measure of how dependent two variables are. We can look at the L2 distance between the true distribution of the data and the product of the marginal distributions of the data. This is 0 if and only if the data are independent. And we think of distributions where this is large as having a strong dependence between the two variables. And we think of distributions where this is small as having a weak dependence between the variables. So we can define alternative hypotheses like this, and then given a test, we can study how powerful this test is by asking how much separation do we need between the null and alternative hypotheses in order to have satisfactory power. This is called the minimax separation radius for the test. And then we can look for a test that has the smallest separation radius. So we can look for a test which only requires a small separation in order to have good power. This is a kind of fairly standard minimax framework that can be applied to lots of different hypothesis testing problems. In the context of independence testing, results on this kind of framework have been studied previously. So in this first point here, we have some references for the univariate problem. So I talked earlier about how the univariate problem is a bit simpler than the multivariate problem. And as far back as the 80s and early 90s, there were results by Ingster and Ermakov, for example, finding minimax rate optimal tests for the univariate problem in frameworks similar to these. The first results that I'm aware of to study minimax rates of convergence for multivariate independence testing are these in the Albert et al. Paper from 2019. They're excellent results, they're very nice. The slight drawback is that they have to impose smoothness assumptions on the null hypothesis, and they get a critical value for their test by looking at concentration inequalities, bounds on certain moments, things like that. And so the tests that they actually study in theory are only valid under certain assumptions that are not verifiable in practice. So kind of one way of seeing our work is us trying to extend these results to also hold for permutation tests and tests that are known to be valid without any assumptions. I think this is a very nice starting point for a paper, and of course I had this idea and other people also had this idea that this would be a nice idea for a paper. So while we were doing this, Kim Balakrishnan and Wasserman were also doing something similar, and they were studying the minimax rate optimality of another permutation test, this time based on the Hilbert-Schmidt independence criterion. Okay, so just a kind of preliminary result to formalize this notion of hardness that I talked about earlier. So I said earlier that when you're dealing with continuous data, there are just so many different ways that variables can be dependent that you need to impose smoothness assumptions in order to have any form of uniform power result. And this is a result just formalizing that. So if we restrict attention to the case where x and y are continuous and they take values in the unit hypercube, then what this result says is that for any sample size and any separation, so any strength of dependence and any test, I can always find some distribution which is in a blind spot for this test. So any test and any sample size, I can always find a distribution for which this test has poor power. And this result rules out any power results that are uniform over the entire alternative hypothesis space. And this is the reason that we have to impose smoothness assumptions. I think that this was kind of heuristically understood previously. It wasn't a huge surprise to us, but this says that we have to impose smoothness assumptions in order to have uniform power results. And the smoothness assumptions that we're going to impose are going to be of a Sobolev type. So if we expand our density functions in some basis for L2, then we can look at a quantity like this, and we can bound this quantity to control how quickly these coefficients in the spaces expansion have to decay. So we say that if the coefficients in this basis expansion decay very quickly, then this is a smooth density. And if they decay very slowly, then we say that this is a non-smooth density. And so we consider classes of distributions where this quantity is bounded. And this is a fairly standard assumption in non-parametric statistics literature. Okay, so there's a lot of formalism there. I hope it doesn't put you off too much. But now we're going to come on to discuss the specific test that we're going to use. So we need to introduce what test statistic we're going to use. I previously introduced this measure of dependence, D of F. This is the L2 difference between the tree distribution and the product of the marginals. And of course, if we expand these distributions in the basis for L2, we can rewrite this as a sum of squared basis coefficients. What we do is we simply estimate D by estimating some subset of these coefficients. So this is where the tuning comes in. Of course, we're going to require some tuning in a non-parametric problem. We select some subset of the coefficients that we're interested in, and we estimate the coefficients using a U-statistic like this. This is the fourth order U-statistic, so this may ring alarm bells for some people. You may be thinking, oh, how are you going to compute a fourth order U-statistic in practice? Actually, typically, we can do this much quicker than order n to the 4. If this subset factorizes in some sense, then you can compute this in order n squared time. And actually, in certain settings, you can do it even quicker than that. So we'll see that in the discrete setting, actually, you can calculate this in linear time. Okay, so this is the test statistic that we're going to use. Once we have our test statistic, it's simple to come up with the critical value. I've discussed this already. We use random permutations and we recalculate the test statistic on the permuted data sets. And then we calculate the p-value like this. And as before, this gives us a uniformly valid test of independence. To specialize this to the discrete case, if we suppose that x and y take values in these finite sets, then we can rewrite the test statistic in a simpler form. So we have this term here, which is like the L2 difference between the observed contingency table and the expected contingency table. Similar to how you would apply the chi-squared statistic. We have another correction term here. And then actually we have some other terms that only depend on the row and column totals. Now, the reason that I'm omitting these terms is that these terms do not change under permutation. So when we compare the true test statistic to the test statistics computed on permuted data sets, these terms always cancel out. And so we never actually need to compute these terms. This is just a quick note to say that you can very easily calculate a kind of permuted contingency table. So you don't need to unwind the contingency table into a list of observations and permute the y values. There are ways to work directly with a contingency table to generate null tables, and they're called, one way of doing that is Papefield's algorithm. Okay, so this is the statistic in the discrete case, and the corresponding power result that we prove is that the minimax rate of convergence is the parametric rate of convergence. So this is a fairly simple problem. Actually, in the discrete problem, we don't require any smoothness assumptions at all, at least when the problem is set up in this way. And we see that if the L2 difference between the true probability mass function and the product of the marginal mass functions is at least n to the minus a half, then we can have power. And of course, being the parametric rates, this is optimal.
So, Tom, so in your distribution function, do you assume bit J and bit K to be bounded?
No, no, we don't have to do that. This is kind of because we're measuring the dependence in L2. I think if we measured dependence in L1, then it would be a different story and the size of the table would come into it. But if you measure distance in L2, then it's not necessary to bound these.
Okay.
Okay, so yeah, if you measure dependence in the L2 norm, then the parametric rate applies. You get a rate of convergence of n to the minus a half. Of course, when we're talking about rates, you often worry that there could be arbitrarily large constants and things like that, but actually that doesn't happen here. Just to give one result that says that this is quite a sensible estimator. This is in fact the minimum variance unbiased estimator of D. So even down to the level of constants, we have a good estimator here. And just to give a quick simulation example, we can compare this test to the chi-square test for distributions of this form. And actually the black line here is the power of this new test. And you can see that it's higher than both the chi-square test and the likelihood ratio test, and also the permutation versions of these tests. Of course, this is only for this distribution, and you can find other distributions where the chi-squared test is better, but just to say that this is a test that can have some practical value as well as being a theoretical tool to prove minimax upper bounds. Moving on to perhaps the more interesting setting, which is the setting with continuous data. We find in this case that we do have to impose smoothness assumptions. Of course, this is what I said before, and we're imposing a Sobolev smoothness condition, and we're expanding our densities in the Fourier basis. So we define our alternative hypothesis to be all those smooth distributions whose dependence is at least some level rho squared, and where the densities are all bounded. This bound on the densities, we're treating that as a constant, and I kind of think of this as a technical assumption, but we had to make it to make the analysis tractable. But what we show in this continuous setting with the Sobolev smoothness is that the permutation test I've introduced achieves this separation radius. Okay, so we'll see later that this is actually the minimax optimal separation radius in both R and N. But this is a kind of fairly standard minimax rate. So those of you that are familiar with kind of minimax non-parametric rates of convergence will probably recognize this rate. You can see that for smoother densities, the rate of convergence is quicker. For higher dimensions, the rate of convergence is slower. And yeah, we show that the permutation test achieves this rate of convergence. I just have quite a quick simulation study just as a kind of sanity check to check that this does do something useful in practice. We can consider distributions of this form where there's a kind of sinusoidal dependence between the x and y variables. And the reason it's interesting, or the reason I find it interesting to consider these distributions is that these distributions, as you vary the frequency omega, kind of the strength of the dependence here is fixed, but the frequency at which the dependence occurs becomes higher and higher, and the dependence becomes more and more difficult to detect as omega increases. Almost all sensible methods for independence testing lose power as omega increases. And of course, ours is no exception here. We choose which frequencies that we want to look at. And if the dependence occurs at a frequency higher than the one we're looking at, then we get no power. But if the test is tuned correctly, then we can have quite high power here. Okay, now both of the results I've talked about so far are consequences of a general upper bound. And that is as follows. So I won't dwell on this too much, but the main feature of this probably is that we're decomposing the bound into a bias term and the variance term. If you're interested in the technical details, I'm happy to talk about this further, but I'll probably just say for now that this is a decomposition into a bias term and a variance term. And we get this by bounding the bias and variance of both the original test statistic computed on the IID dataset and also the null statistics computed on the permuted dataset. So the main technical challenge here was to develop theory for bounding the mean and variance of U-Statistics calculated on permuted datasets. The theory for standard IID data is well known, but it's more difficult when you're dealing with non-IID permuted datasets. This is just saying, so this is a general bound here for a general tuning set, but we're saying here how you can choose this tuning optimally. And just as an aside, I won't go into this in much detail, but it is possible to choose this set adaptively. And we can see that we pay a log penalty here. So in some generality, we get this log penalty here. Yeah, so it is possible to do this stuff adaptively. Okay, let's talk a little bit about the lower bounds. So I'm going to focus really on the continuous case here because it's simpler to discuss, but there is more in the paper if you're interested. On a technical level, actually, we're bounding below a slightly different notion of the minimax risk. We're bounding below a smaller notion of the minimax risk, so it's important that it's smaller. This risk is always less than or equal to the standard risk we're using, and the difference between these is that in this risk, we only look at the type 1 error at a single element of the null parameter space. And yeah, we don't control the type 1 and type 2 errors separately. We don't control this at level alpha and this at level beta. We just combine them. And when we show that the lower bound matches our upper bound, one consequence of this actually is that the testing rates are the same for the composite null and for the simple null. So controlling the type 1 error over the entire null space is not, in a minimax sense, is not significantly harder than controlling the type 1 error just at a single element of the null hypothesis. This is kind of the most technical lemma that I'm going to show you, so don't worry if it doesn't look very nice, but this is how we generate the distributions that we look at in our lower bounds. We start with the kind of the constant density, and we add Rademacher multiples of basis functions. So we create a prior over the alternative space, and of course we have to bound the total variation distance between these alternative distributions and the null distribution, and we can do that as follows. If we can do that, then we try to minimize the fourth moment of these coefficients while maximizing the second moment in order to establish a minimax lower bound. The difficulty here from a technical point of view is to control this quantity here, this probability that Q is greater than or equal to 0. When we generate a function in this way, there is no guarantee that it is non-negative. So there's no guarantee that it is a probability density. It's quite a difficult technical challenge to prove that this is a density with high probability. And that's why our lower bounds do not hold in full generality. So in the continuous case, we can do this and we can apply specific techniques. We can apply kind of empirical process techniques to show that to bound this probability for the Fourier basis, and we can therefore get a matching lower bound to go with our upper bound in the continuous setting. But to do this in full generality is quite a challenge. There are other examples where we can do it. We can certainly come up with matching lower bounds in the discrete case, and we can come up with matching lower bounds in some infinite dimensional settings. But in general, this is quite tricky. But in the continuous case that I am most interested in, we can get something that matches in R and N, at least provided this right-hand side tends to 0 logarithmically in the sample size. Okay, so that's just a quick note about the lower bounds. Let's talk a bit more now about some distributional results. So as I've said previously, these minimax testing radius results are based on first and second moments of true and null test statistics. We were interested in proving something a bit more detailed. And what we're doing really is we're doing normal approximations. So at a high level, what we do is we prove that the test statistics computed on permuted data sets have a roughly normal distribution, and so does the test statistic computed on local alternatives. And so we can kind of we can get a fairly simple power function for this test. And now this looks quite similar to the result that Höfting proves, and which has been widely used for permutation tests, but we're proving something similar here with finite sample bounds. But essentially we're showing that the power function of this permutation test is approximately given by this quantity here, where we have the normal CDF, we have a signal to noise ratio, and we have an order statistic. We have an order statistic of a standard normal sample, which is coming from the permuted test statistics. So how do we do this? Our test statistic is a U-statistic, but moreover, it's a degenerate U-statistic under the null hypothesis. So what that means is that if you fix any one of its arguments and take expectation over the other ones, then you get 0. And also, although it's a fourth order U-statistic, it can be approximated by a second order U-statistic. So that's kind of the first step in the proof, is we show that this test statistic is approximately equal to a second order U-statistic. And then we try and study the approximate distribution of the second order U-statistic. So there is a standard theory about limiting distributions of U-statistics. It's quite well known. The most standard results for second order U-statistics, second order degenerate U-statistics, say that the limiting distribution is some weighted sum of chi-squared random variables. But previously I said that the approximate distributions were all normal. So what's going on here? Well, what happens in our situation is that this kernel function h is not fixed as the sample size changes. So if you recall, our kernel is like, we're estimating some subset of the basis coefficients. But as the sample size increases, we're going to increase this subset. So we're estimating more and more coefficients. So in our setting, the kernel changes with n. What that means is that these eigenvalues, these lambda j, change with the sample size. And so actually, we go from something that looks like a chi-squared distribution to something that smooths out into looking more like a normal distribution. So the reason I include this is sometimes people are surprised when you say that a second order degenerate U-statistic is approximately normally distributed. And the reason this happens is that the kernel of the U-statistic is changing with the sample size. This is a phenomenon that is well studied in probability literature and in statistics as well. This is a kind of typical result that you have. So if we have a degenerate second order U-statistic, you can bound the Wasserstein distance between its distribution and the standard normal distribution like this. Again, note that this right-hand side would not tend to 0 if the kernel were fixed. If the kernel were fixed, we would not get a normal approximation. But for certain kernels that change with the sample size, we can get a good normal approximation. So this is the state of the literature for standard U-statistics. But of course, what we need to do is we need to do something similar for U-statistics calculated on permuted data sets. And that is much more difficult. So we prove analogs of this result for permuted data. And this is one of them. Actually, we need something even more involved, because actually we're interested in the joint distribution of a whole load of permuted statistics. I'm just including this one here because it's simpler to look at, but this result here is saying that even if you compute your U-statistic on a jumbled up data set, then you still get approximate normality as long as you can control the required quantities on the right-hand side. Again, this is in the Wasserstein distance, and we prove this using Stein's method. But this has a similar form to the previous bound. So we have a G function here and a fourth moment of H. We have both of these terms here again, and then there's another term that comes from the permutations. Okay, so then let's just put all that together into a specific example. So let's consider the univariate problem with continuous data where we're using the Fourier basis. First, we calculate what the signal to noise ratio is. So that's the expected value of the true test statistic divided by the standard deviation of the null distribution. And that can be approximated by this quantity here. We're using our distributional bounds, so our bounds on the Wasserstein distance. This is a quantity that appears on the right-hand side, so that if this is small, then our approximations are good. And we put everything together and we show that the power of our test can be approximated by this quantity here in a finite sample way. Just to give a simulation, just to as a kind of sanity check, really, the black curve is what would be predicted by the theory, and the red dots are what we see in a simulation study. Okay, so I'll just wrap it up there. What have we done? So we've studied independence testing via permutation tests, and we've given quite a general upper bound on the minimax separation radius. In examples of interest, so for example, with continuous data or with discrete data, then we've given lower bounds to show that this upper bound is optimal. And then we go a bit further and we prove some more detailed power results based on distributional results for these U-statistics calculated on permuted data. Thank you very much for your attention. The main reference here is this one at the top, but we have some further discussion of the discrete case in a newer reference at the bottom here. So thank you very much, and I'm happy to take any questions.
Great, thank you so much, Tom. And any question from the audience? It's a great talk. And actually, I myself have a question, so maybe I can ask while people are composing their questions. I'm wondering, like, when you mentioned about the adaptation, I think a key for the continuous case is the size of M and the choice of this curly M, right? Yes. So I think when you mentioned that, I think I can see that if we know, let's say we know the smoothness is constant, then we can probably easily to choose that. But in order to, suppose we don't know that in practice, I guess you might have some ways you can actually choose your adaptivity from the data, I guess.
Yes, it's the way we do it is essentially a kind of Lepsky's method thing. So this is the kind of standard approach to doing this kind of adaptivity. And we show that there's just a log penalty here. In fact, under stronger assumptions or with a more detailed analysis, it would be possible to improve this. Actually, in the Kim, Balakrishnan, and Wasserman paper that I mentioned earlier, they improve this to a log n factor, and that's because they use stronger concentration inequalities. So for us to show this adaptive result, in some generality, we just use means and variances of our statistics. But if you prove proper sub-Gaussian concentration inequalities, then you can improve this log n to a log n.
Oh.
But yeah, this is a fairly standard Lepsky's method argument.
Okay, great. Questions?
But for estimation, we know the Lepsky's log n is optimal. So that means in testing, Lepsky may be improved. Is that?
Yeah, this is something that I didn't know about before until I read the other paper. But yes, it seems that for testing problems, at least for this testing problem, yeah, you can get an iterated logarithm penalty. I think it's a really nice observation, and I didn't know about this before.
I don't know.
Yeah,
that's impressive. I was a little bit surprised when you in doing the power function. So you actually can show. So if my understanding is correct, under both null and alternative, you have Gaussian approximation. Or at least for the
it's for kind of local alternatives. So not all alternatives, right? Yeah, thanks. I should have made that clearer. Yes, when we have the quality of the approximation is kind of governed by this quantity here, and there is a term here that builds in the dependence. So you only get this normal approximation when the dependence between x and y is weak. If you're looking at kind of alternatives that are separated from the null by some constant amount, then you would get this more chi-squared limit. But when we're establishing these separation rates, we're typically interested in things that are close to the null hypothesis, and for those distributions, we do have approximate normality.
Right, but it is still something so we will for sure analyze the local power. So something I was a little bit surprised. So I'm just making a comment. I'm surprised to know that in your case, the sharp threshold happens when the test statistic is asymptotically normal. So usually, in my world, that will happen when you have a shifted weighted sum of central test Y distributions. So, but in your case, it seems to be different.
Yes, it depends on the test statistic. I know that, for example, for the Hilbert-Schmidt independence criterion, if you have a fixed kernel, then the results on the null distribution of that statistic show that it is a sum of chi-squareds for the null distribution. So for certain test statistics, you do get this chi-squared null. For this test statistic, you get a normal null, and that's it's because we're spreading out and looking at more and more different coefficients, and there's some kind of averaging that's going on to give us something that looks more normal than chi-squared.
Right. So usually when we saw a degenerate become non-degenerate, that is the time the power is strong enough. Maybe too strong so that you have non-degenerate. But when it is on the threshold, usually it's still not asymptotically normal. But in your case, it's different. So
it is still degenerate, but it's degenerate and asymptotically normal.
That's asymptotically normal. Right, you are right. Yes. When we say strong enough, usually that's the time when the first order term pop up. So in your case, it doesn't pop up.
So
but still the second order is.
If you look at, so this is the kind of standard sum of chi-squared variables that you get. But if you imagine the situation where the first n of these lambdas are equal to 1 over n, and the rest of them are equal to 0, then as
I know this result. It's Peter Hall's result, 1983. Yeah, martingale. Yeah, that's very neat. I was just, yeah, they are all commons. I mean, I learned something. I don't know these two phenomena before. Thanks.
Thanks.
Okay, great. And other questions for Tom? Okay, well, I think people are probably exciting about, it's Friday, it's the weekend. So if no other question, that's thanks Tom again. And yeah, thank you again for this really wonderful talk. And hopefully we'll see you soon in the future in person.
Yeah, well, thank you again for the invitation. Yeah, it was good to see you.
Okay, thank you. See you.
Thank you. Bye.
Bye.